so we had the lab for unit 1. Lab day was Monday. And we should have at least worked on our binary numbers. Some people did not have multi-sim, and hope everybody has it now. Okay, I will still work with Push IT to, they have the remote system set up, but not multi-sim on the remote system because there's some certificate or licensing issue that they have to work out. But I will try and keep on top of that. So if anybody ends up stuck at home, they can get some work done there. Okay, so we had started unit 2, the lecture, a little bit last week when we were online. There's John. Okay. And that's what I'm going to continue with, the lecture from unit 2, but I'll ask if there are questions. Any questions you want me to address before I start lecturing on continuing the lecture on unit 2? Okay. All right, so we were somewhat into this. Where the silly bull cartoon. I think I remember AB is not AB. I think we did that. I think we did this, but not. I think that's where we ended. Anybody remember? We talked about this. No. All right. I don't think we started talking about truth tables. Okay, good. We've got a good memory. All right, so a truth table. So that was a truth table. This thing is a truth table that we're doing here to sort of show that these two things are not the same. We did it by showing that they don't have the same truth table. So a truth table is going to have two sides, an input side and an output side. And on the inputs and the outputs are Booleans, are either true or false, sort of hence the name. You have a table of things that are true or not true, hence the name truth table. And on the input side, we're going to figure out how many inputs we have, and then we're going to write down all the possibilities of combinations of true and false. I'm going to usually write 0 and 1. In electronics, we can also think of them as high and low. But I'll write 0 and 1. That's the easiest thing to write. And then the outputs are for a particular situation. So the input side is just all the combinations. You can arrange your combinations in different orders, but you must have all of the combinations. There are times when we leave ones out that we say we just don't care about. Like, oh, that's never gonna happen. We don't care about it. And so when we get to a situation like that, I will point it out. But normally in a truth table, we have all the possible inputs. It's possible the order of the inputs, the order of the arrangements doesn't matter. So we can start off, I will start off with 0, 0, 0 if I had 3 inputs. And if you were over in the discrete math class, they would start with T, T, T. True, true, true. So they use T and F, whereas I use 1 and 0, and they start off with all truths, which for me will be a 1, so they start off in the opposite direction than I do. And that doesn't matter. And if it does matter, they're wrong and I'm right. So then, all right. But the output side, and this is what throws people, is that the output side can change. It's different. It's a situational thing. There's some scenario, And then for that scenario, here are the outputs. And then there will be a different scenario and there will be different outputs. And people think that, you know, in the beginnings, there's some people who think that there's one set of outputs and then they're done forever and ever, and that's not the case. All right. So I'm going to take, again, we can talk about true and false, high and low, 0 and 1. I'm going to work with zeros and ones. And our convention will be that high and true and 1 are equivalent. And then, of course, 0 and false and low. And that's just a convention. And its convention will almost always follow in this class, but it is a convention. You can have a circuit and you can call the high value false. It's just a matter of, you know, there's some physical situation and you're giving it an interpretation. This is the interpretation I will normally give it. All right. So we have to write out all of the possible inputs. I'm going to work with zeros and ones. And then I have to write down for however many inputs I have. I am going to write out all the combinations. And the easiest way for me to write out the combinations is to count in binary. So learning about binary numbers was setting us up for truth tables because our inputs are going to be the different numbers. We know each number is distinct. So the combination of the zeros and ones representing it must be unique. And I know how many combinations there are because we played with binary numbers and we said if there were 3 digits, 3 bits, then it was 2 to the 3. So there were 8. And I get that by counting from 0 to 7. Okay. Then we need to write an expression for, so I have the truth table. I have the input side, all the combinations. I have the output side, the highs and the lows, the ones and the zeros for whatever situation I'm dealing with. And then I can write an expression for that particular scenario, for that output based on those inputs. And I can always write an expression that involves ands, ors, and nots. I can do better than that. We'll talk about it later, but let's first get this under our belt. I can always write an expression in terms of and, or, and not. And that's what we want to learn to do today. Okay. So first thing is we want to look at an and see its how some ANDed expressions with just 2 inputs for now. So here's A prime and B prime, and that is a 1 in that first row and 0 in all the other rows. A prime B is a 1 in that second row and 0 every place else. A B prime is a 1 in that third row, and A B is a 1 in that fourth row. So ANDed expressions, if I'm working with the nots and the ands, I can always write an expression that is a 1 in a particular row and 0 every place else. So I can do that in that first one, A prime B prime. If I want to write an expression for a given row, if the A is a 0 in that row, I will prime it. If it's a 1 in that row, I will not prime it. And I have all of the inputs. So right now I only have 2 inputs, so all my expressions involve both A and B. If A is a 0, I will prime it. If A is not if A is a 1, I don't prime it. If A is a 0, I do prime it because I'm trying to make ones. If I put all ones into an AND gate, that's when I get a 1 out of the AND gate. And so I'm trying to make a 1. So if the row has a 0, I want to turn it into a 1 by inverting it, by giving it a prime. Okay. All right, so I can write an expression for each row that involves nots and ands. In the case of 2 inputs, there they are. And now what I want to do is bring in the ORs. And so I'm going to have a more generic scenario. So in those scenarios I just looked at, there was 1, 1, and the rest were zeros. Now I want to bring in a more general scenario, which may have multiple ones. And I want to take those ones of my output, take the outputs that are ones, write their expression that we just talked about, find that AND expression, and then OR them. Put all those AND expressions into an OR gate, and that will be an expression for the whole table. Okay, so here's some example. And again, this is just an example. This is a possible scenario that you might want to build, and it's majority rules. So if I have 3 inputs, A, B, and C, and I might want to say that if 2 or more are high, then I want to get out high, and otherwise I want to get out low. So if I put all my inputs A, B, C in order 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. That's 0, 1, 2, 3, 4, 5, 6, 7. If C is the 1's place, B is the 2's place, and A is the 3's place. They're not, but I can think of it that way to make sure I have all of my combinations. And then here's my scenario, majority rules. So the first guy gives me 0, the second guy 0, the third guy 0, the fourth guy gives me a 1, because there were 2 1s. This guy 0, this guy 1, 1, 1. 2 or 3 1s give me a 1, otherwise I get 0. Just a scenario. It's a scenario we're considering right now, but the scenario will change. Okay. Now, in this approach that we're talking about right now, we look at the outputs. Here are the outputs. I look at the outputs that are 1s, so there are 4 of them. And I'm going to write that AND expression for each of these outputs that are 1s. So here's this first one. A is 0, B is 1, C is 1. So if we're there, A 0, B 1, C 1, that expression would be, again, I'm going to try to make 1s out of everything. So it'll be A prime B C. Right? A prime B C. So if A is 0, but I prime it, then A prime is a 1, and then I would have 1 and 1 and 1, and that AND gate would produce a 1 in that row. Down here for this row, 1, 0, 1, that would be A, B prime, C. In this next to the last row, it's A, B, C prime. And then in the final row, it's A, B, C. So those are the expressions, the AND expressions, the expressions that involve ANDs and NOTs that give me a 1 in these individual rows. There they are now. So I have all the possible expressions, but I'm only interested in the ones where the output was a 1. And then my final step is to OR these things. So each row is represented by ANDing with inverses, or I'll call them primes. And ANDing is like Boolean multiplication. We talked about that. And then the truth table, the final truth table is found by ORing the expressions. So A prime BC plus AB prime C plus ABC prime plus ABC. That ANDing is like multiplication, means that these things we're going to call a product, and then our end result is going to be a sum of products. So we're going to refer to this as the sum of products approach. So we find expressions that are ands, which are like products, and then we make a sum of them. So that is an expression. This, if I wrote out this expression and found its truth table, it would match the majority rules truth table. So this is logically equivalent to the majority rules truth table. So it is an expression for the truth table. It's not the only expression. There are other possible expressions, but this expression, this is an expression. This is one thing we have to learn about Booleans, is that the expression is not unique. Pausing, see if there are any questions. Like this is definitely, positively, absolutely on test one when we have test one. I will give you inputs, and here's my outputs for my made up scenario, and then you will have to write a sum of products expression and then build it in a multi-sum. Okay, another term for this is Minterm. So just another fancy word for it. Now we will learn at some point to simplify and of all the expressions that are possible, try to find one that's simpler. We're not doing that today, that comes later. But when we, Minterm definitely means not simplified. Minterm means I take all my inputs and I may prime them and then I AND them and then I OR them together. So sometimes I will ask you for the Minterm and sometimes I will ask you for the sum of products. And if you simplify, strictly speaking, you're not doing the Minterm. So if I ask you for the Minterm and you simplify, you think you're giving me a better answer and you're actually giving me the wrong answer. Probably won't mark it wrong, but I would, but it is, strictly speaking, wrong. Minterm is like just everything appears in every term. Okay, stuff I stole, okay. Here's what it looks like if you build it in multisim. There are other ways to build it in multisim, but this is my usual way. I have a battery, this 5-volt battery. I have a wire coming out of the 5-volt battery, which is 5 volts. And then I have a wire coming out of the other side of the 5-volt battery, and that's also connected to ground, so that's 0 volts. And so this top wire is my high, and this bottom wire is my low. I have a switch here. I have 3 switches, one for A, one for B, one for C. And A can switch between the low and the high. Right now it's low. The B can switch between the high and the low. Right now it's low. And the C can switch between the high and the low. Right now it's high. It matters how it's connected. Sometimes these switches will be like horizontally oriented. And high does not mean the switch is up. The switch high means that the switch is connected to a high voltage. It's always about the connections and the voltages, not what's like physically higher on the page. That's irrelevant. Okay. Then some of my expressions involve A prime. So here's this A, this whole wire is the same as A, but I take the output, I take a connector off of A and put it through a NOT gate. Look at the little circle, that's a NOT gate. And so if I ever want A prime, here's a line that gives me A prime. This wire is A, this wire coming out of the NOT gate is A prime. Same thing for B and B prime, C and C prime. What was my first expression up there? I didn't give them the same order, unfortunately. This is A and B and C prime. So that's this expression. This guy here is A, B prime, and C. So that's this one. This guy is not A, B, and C. So that's this one. And then this one's A, B, and C. That's the last one. So I didn't put them in the same order. The order doesn't matter. Are we okay? I'm telling you, on test 1, this is 1, it's on the lab. 2, it's definitely on the test. The sooner you get this, the better you'll be in this class. Is there any question at this point? It's not going away. It's not something you can skip. Say, I'll just lose those points because we're going to do it. Another thing like this and another thing like this. So, all right. So here I flip some switches. Now I have A high and C high, but B is low. But in my majority rules, that should be high. And here I have this little probe thing lighting up. Okay. So we have some new things here. You've seen a battery and a NOT gate, at least those people who had multi-sim on Monday. Apologies to those who didn't. There's a switch. That's a new thing. There is a NOT gate. There are AND gates. The gates have a number of inputs. So these inputs, this is a 3-input AND, and this is an OR gate. And it's got a, that's a 4-input OR gate. And this over here is a probe. And it's just a simple little, like, lights up if it's true and doesn't light up if it's false. There are probes that just have little sticks coming out of them. And then there are these color probes that sort of fill in with a color. I like the color ones. It's easier for me to see. I tend not to pay attention to the sticks as much, but the other one's perfectly valid, but just not as clear of an indication to my brain. Okay. Let's do another example to prove that majority rules is not the only truth table in the world. Here's some other truth table. I'm just calling it another example. I don't know what the scenario is, but it's something that came up in my life and I wanted to build it. So I am building it. So here is, these are the ones in this approach. Do I have a truth table? Yes. I have A, B, and C are my inputs. I have all the possible combinations. I have outputs. And I'm going to take the outputs that are true and write expressions for them. So what's the expression for this first one? A prime, B prime, C prime. Because you're trying to make a 1. If you put all 1s into an AND gate, you get a 1. So you're trying to make 1s. So when you see a 0, you prime it. A prime, B prime, C prime. What's this guy? A prime, B, C prime. What's this guy? A, B prime, C. What's this guy down here? A, B, C. And there it is. So again, I took the 1s, I wrote AND expressions. AND expressions are sort of analogous to multiplying or products. And then I OR them. And ORing is analogous to adding or summing. That makes it a sum of products. So we use our primes and our ANDs to make a product expression for each line where the output was a 1. And then we OR them. And again, we remember just the vocabulary. It's also called Minterm. All right. Here's what I call yet another example. So it's the first row was 0 and all the other rows were 1. So can I write this expression? Yes, I can. I can write any truth table. I can write any truth table as a sum of products. So here's a 1, so I would write A prime, B prime, C. Here's another 1, so I would write A prime, B, C prime. Here I would write A prime, B, C. Here I'd write A, B prime, C prime, A, B prime, C, A, B, C prime, A, B, C. So I can, this one's a little tedious because there are 7 of them are 1s, but I can do it. I can write that expression. But we also know from our experience with OR gates that that's just an OR gate. So I could write this mess of 7 products. 1, 2, 3, 4, 5, 6, 7. There are as many terms as there were ones in the output. But I can also write it as an OR, a 3-input OR gate. So this is emphasizing that there's more than one way to write the expression for these truth tables. And we would also, in the long run, like to learn how to pick out the simpler one. So here's a simpler one. So we're going to figure out, we're not going to simplify today. We're just going to figure out another approach. So when there are a few ones, sum of products is nice, but when there are lots of ones, it's a pain. So we want to learn the way when there's lots of ones and only a few zeros. We want to learn how to do that. Okay. So we're going to learn a new technique which focuses on the zeros instead of the ones. So we know that this was A plus B plus C, A or B or C, an OR gate, a 3-input OR gate. And that would give me a 0 in this row and a 1 everywhere else. And then we're going to build up on that. Okay, so now we're going to write the opposite. Before we were doing the sum of products, now we're going to do the product of sums. All right, so now we're going to look for the zeros and write an OR expression and then AND those OR expressions. So we're going to write something that is a sum, which corresponds to OR, and then we're going to make a product of them, which is an AND. Okay, so here are I don't have a truth table, I'm just telling you here the different expressions. If there were a 0 in the first row, that's A or B or C. If I have a 0 in the second row, that would be A plus B plus C prime. Before, I was working with ANDs and trying to make ones. Now I'm working with ORs and I'm trying to make zeros. So how do I make this a 0? I need all zeros. To make an OR expression turn 0, I need all zeros. So this second row here is A or B or C prime. That's when it's all zeros. So that's why I prime it. A or B prime or C. A or B prime or C prime. A prime or B or C, etc. So you're turning the pattern around. It's now we're working with ORs. We want to make zeros. So now when it is a 1, we prime it. Before, you remember before when it was a 0, we primed it because we were trying to make AND expressions to be ones. So we wanted everything to be a 1. Now we want everything to be a 0. Okay. So here is some expression, and I want to write the expression for the zeros. So this would be A or B or C prime. This one would be A or B prime or C prime. This one would be A prime or B or C. And this one would be A prime or B prime or C. Again, I'm trying to make zeros in this approach. So when I see ones, that's when I prime it. I'm trying to make zeros in this approach. So there they are. And then I have a product of them. So there is a precedence in Booleans, the same way there's a precedence in algebra. So I want to form the sums before I do the product. I want to do the ORing before I do the ANDing. And so when I write the expression, I need parentheses, because just like you do multiplication before you do addition, unless you have parentheses, the same thing is true for ANDing and ORing. So that's another reason I like this notation, is that seems natural to us. We're used to that order of operations, that idea of precedence in our regular algebra, and it comes over to our Boolean algebra. So the thing that is like, so if I wanted to perform some additions and then multiply them, I would need parentheses. And that's the same thing if I want to do some ORing and then do some ANDing, I need parentheses. And this approach is known then as the Maxterm. So we can call it the product of sums, because that's what we do. We take these sums and then we make a product of them. That requires parentheses. And we can also say that the vocab term in this case is Maxterm. This is a Maxterm expression. I will, on the test one, when it comes around, when's test one going to come around? We're in unit 2. We're going to have unit 3 and unit 4. That's what the test is on, units 1, 2, 3, and 4. And then we're going to do unit 5 before we have the test. So it's a while away. It's like we have to finish 2, we have to do 3 and 4 and 5, and then maybe have the test. So it's like 3-4 weeks away at least. Okay. And then I will ask you, like, when do you have other tests and other major classes, and I'll try to avoid them if possible. Okay. So again, this is definitely a problem on that test. So the sooner you know it, the better. Here's how you build it. Again, the battery and the high and the low. This time I moved my ground over here. Doesn't matter if the ground appears over here or over here, it just matters where it's connected. Connections and voltage matter. Not particularly, an arrangement doesn't matter so much as the connections. And here I have switch A, B, and C connected high and low, high and low, high and low. Here's the NOT gate, because some of my expressions involve A prime, some of my expressions involve B prime, some of my expressions involve C prime. So this part, here's the good part. I said sum of products is on the test and product of sums is on the test. The battery, the high, the low, the switches, that's always the same. That's the input side of the truth table. It's always the same. And then, so you need the switches, you need the NOTs, you're allowed to bring in circuits for the test. So I would absolutely positively, beyond the shadow of a doubt, bring in a circuit that had a battery and the switches and the NOTs. And then it's only this part that changes. Here, these are OR gates. It's very easy when you're grabbing an OR gate to accidentally grab a NOR gate. Because when you go over to Miss Digital and click on, I think, TTL or something, and you're going down the list alphabetically of the logic gates, NOR becomes before OR in the alphabet. So you're looking for this sort of curly, triangle-y kind of a thing. And NOR just comes up alphabetically first, and you sort of don't notice a little circle on the end, and you grab a NOR by mistake. You've just done exactly the opposite of what you want to do. A NOR is the exact opposite of what you want. You wanted an OR, and you gave me a NOR. You gave me the exact opposite. So here's the OR gate. This is A ORed with B ORed with C prime. That is the first one. This is A plus B prime plus C prime. That's the second one. A prime plus B plus C. That's the third one. This one I found seems to put them in order. And this one is A prime, B prime, and C. I have colored these wires. You can right click on a wire and change its color. That sometimes helps me figure out things. You don't have to do that. This can all be just standard old, I think the standard wires are red, but you can make them black or you can make them magenta, whatever. 10:06, okay. So Maxterms, okay. So here is just one, again, not a truth table, but just the two kinds of expressions on the same table. Okay, we're switching over to resistors. Any questions on the logic stuff before I switch over to resistors? No, okay. All right, so we're going to work with Ohm's law. So if you've played with lab 1, then and lab 1 part C, then you know that if the voltage divided by the current stays the same, if that's always a constant number, if it goes from 2.7 to 2.69, that's not a change. That's a fluctuation or a rounding or something. But if resistance is voltage over current, but if as you change the voltage, which also changes the current, if that ratio stays the same, you have something that obeys Ohm's law. Then the R is constant. So when I call this Ohm's law, that assumes that this R is not going to change. So not everything in the world is like that. Your life depends on something that's not like that. You work with diodes and transistors. They're what give us logic. And they're not like this. The R would change for them. But right now we're dealing with the sort of the simplest component, which is a resistor, and that is where this R is a constant. So in what we're dealing with, R is a constant, V and I change proportionally. So if I double V, I would double I. The voltage is the amount of energy per charge. The current is the rate at which the charges move. So you think about you sit at a point and you watch charges go by per second. And resistance is some measure of the difficulty. So I have a certain amount of energy. I'll often refer to it as a push. The battery gives you a push. And if I have a big resistance, then I will get a little current for my voltage. If I have a small resistance, I will get a big current for my voltage. So it tells me how difficult it is, and then in turn, that will tell me how much current I'll get out of my battery. A circuit is a closed path. So you should be able to get from one side of the battery to the other. Sometimes when we do logic circuits, when we do resistor circuits, we'll stick to this. When we do logic circuits, we will sometimes cheat. Like that, I had that probe, that little light that just lit up on the end. That's not a full circuit, because that should really be some kind of like light emitting diode, and the other side of the light emitting diode should connect like to my ground. So it's not a proper circuit, but we're just worried about the logic right there. But when we're doing resistors, we will be concerned about it being a proper circuit. So it should be closed. You should be able to go from one end of the battery to the other. If there's not a closed path, it's referred to as open or broken. Like if your phone wasn't working or something like that, they might say there's an open on the line or something like that. There has to be a path. There does not have to be a unique path. You can have more than one path. So here's an open circuit. That red wire is not quite connected to the battery. Then when we connect it to the battery, it becomes a closed circuit, then the light turns on. Okay. So the battery is going to supply this force, this energy per charge. And so charging up the battery is like you've had a rested up last night, you had a good night's rest, you're full of energy, and then you're going to use up all your energy in the day. So you had you woke up, you had a good breakfast, you're ready to face the day. And now you're going to use up all your energy and just sort of collapse into bed. So all of your voltage, the quantity we associate with the battery is a voltage, say like a 9-volt battery that you put in your smoke alarm. When you leave the battery, you have 9 volts. And whatever you do in your path, by the time you get back to the other side of your battery, you should have used all 9 volts. You should have nothing left when you get back. Give it your all every day. All right. So if you look ahead at the tasks you have to do today, and you are going to divvy up your energy between those tasks. If you have 2 tasks to do and you give the first one all your energy, then you can't do the second one. So you're going to divide them up, and the more difficult the task, the more energy you're going to give it, the more energy it's going to require. So this is about resistors in series. If my path requires me to do 2 tasks, if it requires me to go through 2 resistors, I have to put some of my energy, I have to use up all my energy, but I have to divvy up my energy and give one of it to one of the tasks and the rest of it to the other task. And I give more of my energy, more of my voltage to the thing that is more difficult. So here is my battery. I'm coming out of my battery as a current. I have 2 resistors in series, R1 and R2. And on the wire before, so this, let's say this is a 9-volt battery. So this, I have 9 volts up till I get to this resistor. Then I'm going to use some of that voltage to get through resistor 1. And then I'll have some other level of voltage, not 9 volts. And then when I go through R2, then by the time I get through R2, I should have 0 volts. So some of my, I start with the full amount of voltage. I use some of it up in R1. I use the rest of it up in R2. So the voltage across R1 plus the voltage across R2 should add up to the total voltage, which I was pretending it was a 9-volt battery. So it should add up to 9 volts. Okay. So this is our definition of series. So the current comes out of the top of the battery. It goes through the first resistor, R1, and then it goes through the second resistor, R2, and it returns. So they see the same current. The current, a charge that comes out here, goes through here, and then must go through there. It's got no place else to go. There's no node or junction here with another way for me to go. If I went through one, I have to go through 2 because I have to go home. Okay. So things in series, those resistors were in series, they see the same current. Any charge, current is the charges that are going by. Any charge that went through 1 has to go through 2. They can't accumulate. The charges can't accumulate like between the resistors. That would cause a lot of trouble. And they just don't do that. They're going to go from one side of the battery to the other side of the battery. That's what they're doing. And they don't stop along the way. Okay. So the voltage across the first resistor is, I'm calling V1. Because it's a resistor, it obeys Ohm's law. The voltage across the second resistor is I times R because it's a resistor and it obeys Ohm's law. We know that they are in series, and things in series see the same current. So this is an I1 and I2. It's I1 is equal to I2 is equal to I. And then we know the voltages, V1 and V2, they add up to the total voltage of the battery. Because you got to use up all your energy when you make your path around, and the path involves these 2 resistors. So here's the battery voltage is equal to V1 plus V2. They have to add up. I replace V's using Ohm's law. We note that they were in series, so these currents are the same, so I can factor the current out. And now I have that the voltage is equal to I times R1 plus R2. I'm going to call R1 plus R2 an equivalent resistance. So I could, instead of saying this is task 1 and task 2, I could say they're both parts of one bigger task. And what is the resistance of that bigger task? Well, it's R1 plus R2. So resistors in series add. So I can imagine that there's just an equivalent task, an equivalent resistance, and its resistance is R1 plus R2. So there, that's what we have. So that is the equivalent, the concept of equivalent resistance. Then I can replace two resistors with one that will have the same effect. Or the same voltage, give me the same current. That's what I mean by the same effect. But it's, so I'm going to replace two with one, but the resistance must change. And what must the resistance be? R1 plus R2. All right. So resistors in series add. The equivalent resistance is larger because if you have two tasks, then it's harder than if there's just one thing, and they see the same current. Okay, so here is my simulation with 1 and 2 in series, and 1 and 2, when I add them, gives me 3. I'm good about math like that. And you see that the voltmeter is reading the same amount of current, 1.667 milliamps. When you report to me a current, this guy, this is an old version of the program, and it puts the M and the A next to each other. In the current version of the system, the M and the A get a little bit separated. But you must always, if there's an M, you must report it to me, otherwise you're wrong. If I have a table of things and have an M at the top, I want it to be in milliamps. And then if it doesn't be in, if it's not in milliamps, you better convert it to milliamps. If I give you a table and there's an empty set of parentheses at the top, that means you're supposed to put in milliamps. And if you don't, then you reported a number without a unit and I'll mark it wrong. Or at least I'll take off some points. Okay. So again, all of this talk about using up all your energy is about one charge, but the current is going to be made up of many charges. And so how do we talk about that? Well, if the resistance is big, if it's a hard task, then not as many charges are going to go perform it. So then the current will be low. And if it's an easy task, then everybody volunteers to do that task and the current will be large. Okay. If we had more energy, if our voltage were larger, then we'd have more eager people to go out and do the task and the current would be larger. If we have a low voltage, if nobody gets a good night's sleep, then there won't be as many people ready to go out and do the tasks. All right. Next, we're going to move on to parallel. This is the case where there are sort of multiple paths, where there are choices in the path. And so then there's going to be a difficult task and an easy task. And then, of course, more people will choose to do the easier tasks. So when we have a different paths, we expect more people to take the path of least resistance. So we're going to start talking about resistors in parallel. So here is a picture of resistors in parallel. Here's this blue is the battery. When you leave the battery, you have a certain amount of energy and the charges are leaving. They reach this junction. Some of the charges are going to choose to go through R1. Other charges will go through R2. They will rejoin down at this node below, and all the charges will go all the way around. So the current comes out of the battery and then it splits up. So some of the current goes through R1, some of the current goes through R2. So the currents are going to add. I1 plus I2 is going to add up to the total current I. Each one of these, there's a path here through R1. There's a path here through R2. On a given single path, the voltage must be used up. So the whole voltage must be used up on R1 if I take that path, or the whole voltage must be used up in R2 if I take that path. So things in parallel see the same voltage. So I have some energy, there's a voltage level on this wire, there's a voltage level on that wire. I need to use that voltage up, whichever path I take. And so they see the same voltage, but the currents are split up and the currents will add up to a total current. Okay. So again, here it is more diagrammatically with the resistors represented by the zigzag line, the battery represented by these long and short lines. Here's the ground. If there's a connection of wire on one side, right now I'm calling it the top, and a connection of wire on the other side, then those resistors are said to be in parallel. They can be, that connection, that combination can be connected to other things, in this case a battery, that's okay. But if there's a connection of wire on one side and a connection of wire on the other side, that's what makes us parallel. I will give you more complicated circuits than just two resistors in series or two resistors in parallel. I'm going to give you circuits with, I don't know, 7 or 8 resistors all over the place. And you're going to have to identify, oh, these ones were in series and those ones were in parallel. So you need to understand these definitions. All right. So the voltages were the same. When you're on a wire, the energy, you don't use up any of your energy on a wire. Yeah, ideally, you don't use up your energy on a wire. So there's the same energy here as here. And then as you get back here, they should also have the same energy here because they're, again, connected by wire. You don't change your energy on a wire. So this voltage and that voltage should be the same. V1 is equal to V2 is equal to V. And the currents add. Some of the current goes this way, some of the current goes that way, but they add up to the total current and then they add back up after. So the voltages are the same, the currents add. The resistor was doing the opposite. When we had series, the voltages add and the currents were the same. When we have parallel, the voltages are the same and the currents add. So we start off with our current. We could call this the conservation of current. The current has to come into the situation, but it doesn't stop there. It has to just split apart and then get back together. So the current, the total current is I1 plus I2. We're going to put in Ohm's law, solve for current, which is V over R. So it's voltage over equivalent resistance. We're working with this idea of equivalent resistance. And then it's V1 over R1 and V2 over R2. But we said all those V's are the same. The V of the battery and the V seen by R1 and the V seen by R2, they're all the same. So it's V, V, V. They divide out and we're left with just ones in the numerator in place of the V's. So we factored out the V, leaving us with the 1. The R's were in the denominator. So when we get rid of our numerator, we have to have something left in the numerator. It was a 1. So here's our formula for resistors. The equivalent resistance of resistors in parallel is this reciprocal addition. All right. Resistors in parallel add reciprocally. The equivalent resistance is lower. The resistance will go down compared to either individual one. And it's always easier if you have a choice. So you are going to, if you have the choice, then you make, more people will make the easier choice, but overall for the whole system, it will be easier. The resistance will go down. So here I added 2 kilo ohms and 1 kilo ohm in parallel. There's a connection of wire on one side, there's a connection of wire on the other side. They're parallel. I did that reciprocal addition. I ended up with 2/3. When I finished off the job, I made the circuit with the parallel resistors with the equivalent resistor and got the same current. That's what we mean by equivalent resistance. And it gives you the same, for the same voltage, it gives you the same current. So that's the sense in which it's equivalent. Okay. How to do the math. You can do the math any way you want to do the math. I'm showing you a way to do the math. The calculator that's on most computers has a reciprocal button. So if I had 2.3 and 3.4 in parallel, then I can type in 2.3 and then hit my reciprocal button. Then I can hit my plus button. Then I can hit 3.4 and my reciprocal button. And then I hit the equals to perform the addition. And then I perform one more reciprocal. So the formula has 3 reciprocals, one for R1, one for R2, and one after you've done the sum. And so you put in a number and a reciprocal. And then that guy's ready. And then you do a plus and a number and a reciprocal. And now that guy's ready. You perform the equals to go back and actually execute the addition. And then you need one final reciprocal. If you know a different way, if you can use it. I don't care. But this is, I've taught you a way that's fairly simple, and the calculator has the button right there ready for you to use. All right. I've been asked in the past if, like, you have these two resistors in parallel, why don't just all of the charges take the easy way out? Why don't they all go through the easier resistor? And the answer is because that's not the best thing to do. And now we'll do the fire in the theater analogy. So you go to the theater in non-pandemic times and somebody yells fire. There better really be a fire, or that's like, you're not allowed to yell fire in a theater. That's not part of free speech. So there better be a fire. Now everybody's got to get out of the theater. So in the back of the theater, there are this big set of doors, very wide open, very easy to get through. They have a low resistance. And then down in the front somewhere, there's like the emergency exit, just one little emergency exit down in the front. Harder to get through. Not as many people can get through that. But when we have to get all these people out of the theater as soon as possible, it is easier for at least some of them. Not everybody's going to go through that little emergency exit door in the front, but some will. Because when we talk about what's easier for one charge, we're ignoring all the other charges, but we can't do that. There are all these charges, they're interacting with each other. And so they just can't all do what's easiest for them if they were alone, because they're not alone. And so it will be easier in this theater analogy for at least some people to go through that other exit and not wait behind the crowd to use the back exit, even though that's an easier entrance to get out of. Series is the same current. The voltages add up, the equivalent resistance is R1 plus R2. Parallel, the resistances see the same voltage, it's the currents that add up, and the equivalent resistance uses this reciprocal formula. We also have the concept of series and parallel in computer science. We send bits serially. It means that there's sort of like one wire and you must send bit by bit over the wire. So they all follow the same path, just like resistors in series. Or we could talk about doing things in parallel, where there are multiple paths and it's sort of shared. So again, there are things inside the computer down at the processor level that are parallel. there's not much in an old computer. This is an old picture, so there was a serial port and a parallel port. But you won't find most of the peripheral things these days are all serial. And only when you get down to like the processor level will you find things in parallel. So, but it doesn't mean that parallel and serial don't exist anymore. We still talk about things at the processor level are still in parallel, but everything sort of outside of the processor ends up to be serial. But we also have the concept of overall parallel computing, splitting things up among different computers, which has an analogy to this idea of parallel resistors. Splitting the job up, it's always easier. Okay. We have a multimeter concept. If we were doing a more real class, a physical class, where we had real resistors and we're doing real measurements, then I would hand you not a voltmeter, an ammeter, but I would hand you a multimeter. And you would turn it into a voltmeter, you would turn it into an ammeter. Oops. And voltmeters go in parallel. Things in parallel have the same voltage. And so if you want to measure the voltage of something, you want your meter to have the same voltage as the something. And so then you want it to be in parallel. They share current. So you're changing the current a little bit, but the point with a voltmeter is you'll try to change the current as little as possible. So you try to get just a teeny bit of current to go through the voltmeter. So you give it a big resistance. So if you bring out a voltmeter, you'll see that it has a little resistance reading on there, and it's usually quite large, like mega ohms. If you want to measure a current, you would set up your multimeter as an ammeter, and ammeters get put in series. Things in series see the same current, so you want the meter to see the same current as the resistor, so you put it in series. And you don't want to affect that current, so you try to make the resistance of an ammeter very small. So when you pull out an ammeter, you'll see a little reading on there about what the resistance of the ammeter is, and it's supposed to be quite small. And usually I don't ask you to change the resistance of the voltmeter or the ammeter. Maybe once in the semester I will. If you wanted to set up the, I keep doing that. If you want to set up the multimeter to measure resistance, then you want the meter to sort of supply a voltage and then measure a current and calculate a resistance. That's what resistance is. Then you remove it from the circuit. You want the meter itself to be supplying the voltage and measuring the current. And so you remove whatever combination of resistors you want to measure the resistance of or equivalent resistance of. You move them from any other part of the circuit. You don't want a battery involved. So here I am with a voltmeter in parallel. Here is an ammeter in series. And then if I wanted to measure the resistance of those two resistors in series, I would remove the rest of the circuit. I would take away the battery, take away the ground, and just connect them to the multimeter. Okay. Let's say you're having some problem with some device that is connected to your computer, or you're inside your computer and you're worried about something not working. There are all sorts of connections, things external to your computer or things internal to your computer. And when something's going wrong, an easy thing to test for is, do you have a connection? Do you have continuity? So that's just, you're asking, the wire's just a piece of metal. It should be a conductor. It should have a low resistance. So if you want to see, before you go buy new parts or something like that, maybe it's just a bad connector. That would be an easier fix. So if you have a cable and you want to see if the cable's good before you see if anything else is more complicated, has a problem, to check the cable, you take your meter, you set it up as an ohm meter, and you just put the probe, the lead on one on each side, and you're expecting a low resistance. If you get a low resistance, then it is a good connector. If you get a high resistance, then it's not a good connector, and that's your problem, or it's one of your problems. We said we had energy when we left the battery, and then we went through our paths and came to the other side, and we have a lower energy. But in physics, we have a concept of conservation of energy, or better, matter and energy, but let's just talk about energy. So the energy is not lost, it just goes someplace else. And typically the someplace else is that it becomes heat. So sometimes you want the heat. So I have up there the picture of the toaster. So a toaster is basically just a bunch of resistors, and you plug it into the wall. So you have some energy coming from the plug in the wall. That energy is going to be used up. It's not going to go back into the wall. So the energy gets used up. And normally energy, especially when you're going through resistors, the energy becomes heat. When it was a light bulb, some of the energy becomes light. And some of the energy here in the toaster is becoming light because you can see it glowing red. That means some of the energy is light and some of the energy is heat. All right. We don't like in our computer logic circuits, we don't like heat. Heat is our enemy. So if things get too hot in your computer, then you have a problem. So we said that I've told you that the logic part of your computer is not resistors, but something that doesn't obey Ohm's law. But those parts of the computer are even more sensitive to like these heat problems. And so you put in a resistor in a logic circuit, even though it doesn't, the resistor does nothing in terms of logic, but you put the resistor in a logic circuit to take the brunt of any amount of energy, so that the energy is not trying to be used up in the logic part of the circuit, which might burn it up. All right. And we're done. And I have a few minutes to spare. Are there questions for the recording? No.